In this video, we'll review the nitration electrophilic aromatic substitution reaction. So this is called the nitration reaction because we are adding a nitro group. And if you remember from our nomenclature video, that's the NO2 group. And that's what we're introducing to the ring in this mechanism. So we'll start with a benzene ring again. Again, I'll highlight just one of the hydrogens. And the reagents required for the nitration reaction is nitric acid, HONO2, and then we do need a catalyst, but in this case, it's not a metal catalyst, we're using a strong acid. So here I have sulfuric acid, H2SO4. And then this will generate nitrobenzene, where one of the hydrogens on the benzene ring is replaced by a nitro group, NO2. And then a byproduct is water. So a couple things. Do you want to talk about this nitro group, NO2, and what that structure really looks like? So if we have a R, let's just do a NO2 group just bonded to an R, so carbon chain. What this really is actually a resonance stabilized group that has a charged nitrogen and a charged oxygen. So this is that R group's bonded to nitrogen. It has a double bond to one oxygen and a single bond to another. That oxygen has a negative charge and the nitrogen has a positive charge. And so this is resonance stabilized because we can create a double bond there and break the other double bond. Nitrogen stays positive, but the oxygens, either one can hold the negative charge. So when we're talking about an NO2 group, that's the actual Lewis structure that we're looking at. And then another thing to think about is, I said we add nitric acid, but then we also need an acid catalyst. So if we already have an acid, why do we need another one? Well, the pKa of nitric acid is negative 1.3. So that's a pretty strong acid, but it's still not quite as strong as H2SO4, which has a pKa of negative 9. So we use H2SO4 to make the nitric acid a better electrophile. And so we'll do that in the first step of the reaction where we are generating the electrophile. When you see H2SO4, that's often what it's used for, is to protonate something to make it more reactive. And that's exactly what we're doing here. So the structure of H2SO4 is a sulfur bonded to two OH groups and double bonded to two oxygens. I'm showing one of the bonds to a hydrogen, from oxygen to a hydrogen, because that is the acidic proton. So when this is in the presence of nitric acid, we draw out that Lewis structure. It looks like this. In nitric acid, the oxygen that's bonded to a hydrogen is weakly basic. So that will be protonated by that oxygen. By that hydrogen from H2SO4. Now remember, this pKa is -9. This pKa is -1.3. So H2SO4 is a stronger acid. It donates its proton. So this generates our electrophile. Well, it helps generate our electrophile. Okay, we have two positive atoms next to each other in this nitrogen-oxygen molecule, and that's pretty unstable. We also have a good leaving group. I'll highlight this. I'll highlight it in purple. Anytime you see this bonded to a molecule, essentially the water molecule, that is a really good leaving group, and that's exactly what's going to happen here. The oxygen that's negatively charged will create a double bond to the nitrogen, and then the bond between nitrogen and the positively charged oxygen will break. So we get water and the nitronium ion. And this is the electrophile that is a strong enough electrophile to then be implemented in the EAS reaction. Looking back, there's one thing I want to add. After this first step, where we protonate the nitric acid with H2SO4, another byproduct here is HSO4-. This is a weak base. All right, we've generated the electrophile, which is the same first step as the halogenation, which we already kind of talked about. Step 1, generate electrophile. And in this case, it requires multiple steps. And then step 2, we form a resonance stabilized carbocation intermediate, same second step as halogenation. So now we're working with our benzene starting material. We have our stronger electrophile, the nitronium ion. . This nitrogen is electron deficient because it has two oxygens that are pulling electron density away from it. It is also positively charged, which is another reason why it is electrophilic. So when we do this mechanism, the pi electrons in one of the bonds from benzene will donate to the nitrogen atom. And then either oxygen can accept pi electrons, so you can show that on the top oxygen like I've shown it here. You can also do it on the bottom. It's a symmetrical molecule, so it doesn't matter. This forms our resonance stabilized carbocation intermediate. One of the carbons that was involved in the double bond has a positive charge. The other one is bonded to that nitro group. Just to follow my reaction arrows from the previous step, that's where the negatively charged nitrogen would be. And then let's not forget we have a hydrogen there. Wherever that, on every carbon we have a hydrogen. So this is another resonance stabilized non-aromatic intermediate. Now, the reaction will tend towards re-establishing aromaticity. And just like the halogenation reaction, we do that by removing the beta hydrogen. We need a base to remove that beta hydrogen, and we can use the HSO4 minus weak base to help remove that. Okay, so this is HSO4 minus. The weak base will remove hydrogen, and then the electrons in that bond will reform a pi bond, which reestablishes aromaticity. So this is step 3. And the product of this third step, we reestablish aromaticity, and we have the NO2 group, which I'm abbreviating here instead of drawing the Lewis structure. We have that bonded to benzene. So we now have nitrobenzene. And then our byproduct is we reform H2SO4, which was our catalyst, which by definition, the catalyst should be reformed in the mechanism, which we have established here.